Hello all, welcome. Today we are going to talk about nuclear fusion. Nuclear fusion is a natural process that occurs in the core of any star. Fusion simply means when two or more things they join together. So in the stars what happens is an atom of hydrogen combines with another atom of hydrogen. Together they form a new atom of helium. So this process also releases a huge amount of energy. In a nutshell, this is what nuclear fusion is, when two smaller nuclei they join together to form a bigger nuclei. Let's look at some of its nuances. So here you can see what is happening is a deuterium atom and a tritium atom. Both are isotopes of hydrogen. They combine together to form a new atom of helium and a neutron is ejected. So deuterium has one proton and one neutron, while tritium has one proton and two neutrons. So as you can see, the total number of proton in this side is 2, helium has 2 proton. They are balanced. The number of neutron is 3, while helium still has 2 neutron, and thus we have this excess neutron here. Apart from this, energy is released in the process. Now the biggest question is, how is this energy released? Like, where does it come from? So what happens is the reactant, let's say this is the mass of reactant, total mass Mr, and this is the total mass of product Mp. So Mr is greater than Mp, or Mr is greater than Mp. It is this difference in the mass which, when you put in the equation given by Albert Einstein, E is equal to mc square, you get the energy released in the fusion reaction. Now one question that might bug you is how does the mass change? So this is more of a stuff of post-graduation physics, but I'll just explain it to you in very simple terms. So what happens is the binding energy of helium nuclei is more than the binding energy of deuterium or tritium nuclei, and it is due to this change in binding energy of the reactants and the product that you get a difference in mass, which ultimately transforms into energy. Now another thing that people are confused between is fusion and fission. So quite simply, fusion is when two smaller nuclei join together to form a bigger one, whereas fission is when a heavier nucleus breaks into smaller ones. So here deuterium combines with tritium. Both are isotopes of hydrogen, so we use the symbol H. I wrote D and T so that you don't get confused. So these two combine to form helium, whereas in fission, uranium-235 undergoes fission to form krypton and barium. So thus, in fission we see a heavier nuclei breaks down, whereas in fusion, two lighter nuclei combine together to form a heavier nuclei. Another biggest difference is that the temperature requirement for fusion and fission vastly differs. So fusion requires temperature in the order of 10 to the power 7 or 10 to the power 8, whereas fission is done at 10 to the power 2 to 10 to the power 3. So there's almost a difference of 10 to the power 5 to 10 to the power 6 in terms of temperature. So these are two major differences between fusion and fission. Now, fusion as an energy source. So this is still in experimental stage. The reason that it is in experimental stage is because fusion reactors, they require tremendous amount of temperature to work on. So at Sun, fusion takes at 15 million degrees. Whereas in our lab, if we want to have fusion, we'll need a temperature 10 times higher than that of Sun's core. So we'll need a temperature of 150 million. Now you can imagine how hot 150 million is. So a doubt might creep in is, why is there almost a difference of an order of 10 between the temperature required at Sun and in our labs? So let me clear this out for you. So what happens is that in Sun, let's imagine this is our Sun. So in Sun, at the core where fusion takes place, it is under heavy pressure. So the entire weight of Sun is applying pressure on its core. And that's why due to this high pressure, the temperature requirement is less. However, in lab, we cannot create this much amount of pressure, and hence we need a higher temperature. Now in this image here, you see a tokamak reactor, T-O-K-O-M-A-C. Now this is one of the most advanced reactor for fusion that we have right now, and it has a strong electromagnet at its core. The purpose of this electromagnet is to create magnetic pressure to confine the plasma in. Now plasma is the fourth state of matter. Basically it's nothing but an ionized gas. By ionized gas I mean the charges are separate. So fusion, when we reach temperature as high as 150 million, the reactants they change into plasma form, and we use this magnetic field to confine this plasma. Inside this chamber we also create a very intense vacuum, so there's pump that creates vacuum, and of course there's cooling system because this system gets very hot here inside this. So this is the basic parts of a tokamak reactor. Now, again, you don't need to know much detail, like knowing that there's a electromagnet that creates a strong magnetic field to magnetically confine the plasma is more than enough knowledge you need about tokamak if a question ever comes in exam about fusion reactors. Now, this whole issue came to forefront when recently China's East is a tokamak reactor, experimental advanced superconducting tokamak, reached a temperature of 120 million degrees, and it sustained it for just over 100 seconds, so it sustained it for 101 seconds. So you can see, like, we have only been able to create this high temperature for such a small time, and to reach the stage where we can produce energy through fusion in a sustainable manner, we need to maintain this temperature for a very long time. Okay, an example of fusion that you would definitely have heard is hydrogen bomb or thermonuclear bombs. Now hydrogen bomb is an uncontrolled fusion reaction, okay, and we don't need uncontrolled fusion reaction, so in the lab we need it to be a controlled fusion reaction. So what happens here is that the reaction continues until the fuel is burnt, and that's why hydrogen bombs are very devastating. They have not been used so far, and hopefully we won't see a time where they are used. Now one might wonder, why do we need fusion when we already have fission? Like, what advantages does fusion give us? Because since you can see that it's a very advanced tech and we haven't achieved it. So the biggest advantage that fusion has over fission is that fusion is clean, whereas fission leaves out radioactive waste. So it poses the challenges of disposing of this radioactive waste, whereas fusion is clean. The reactants are hydrogen or its isotopes. The outcome is helium. The second big advantage here is fuel. So as you can see, since the fuel is hydrogen, deuterium, we have endless supply of that. So we'll never run out of fuel. Whereas for fission, we need radioactive material like uranium, plutonium, which are in very limited quantity, and thus fission cannot be seen as a fuel for the longer run. These are two major advantages that fusion offers over fission. Apart from that, fusion produces tremendous amount of energy compared to fission. So I hope this was clear, and if there's any doubt, please write it in the comment section. Thank you. Have a nice day.